We now prove an example using the contrapositive. So let's consider this statement here. We want to show that if n squared is even, then n is even. Now, the idea here is that if you try to do a direct proof, you start with n squared being even. It might be hard to sort of, how do you deal with the square? I mean, you should try it yourself. You'll see that it'll be a bit of a headache. And so it's actually easier to deal with n than with n squared. And so doing the contrapositive will look easier. So let's see what this looks like. So here, our hypothesis is n squared is even. Our conclusion is n is even. And so we want to prove P implies Q. And this is equivalent to the contrapositive, not Q implies not P. So, not P. So in the proof by contrapositive, what we do is we are going to prove this statement, which is equivalent to this. So if this is will be true if and only if this is true, right? Okay, so now it's essentially a direct proof on this statement. And so how do we do direct proofs? We assume this, do a bunch of algebra, and end up showing this here. Now, it's always good in proofs to start by saying what you're doing. So it's good to start by saying that we prove the contrapositive. So always state what proof you are doing. So then the contrapositive, if I write this in terms of how I wrote the theorem, so not Q, it means that if n is not even, which means that it's odd, then n squared is not even also, which means that it's odd. So I'll just write it. So it is odd. Okay. So we want to show that. So we want to show that if n is odd, then n squared is odd. And so how do we do that? So we start by assume that n is odd, okay? And we're gonna do a bunch of stuff, and we know that at the end, we should end up with, so two things, right? So first, we should end up with something like, therefore, by contrapositive, if n squared is even, then n is even. So we'll end up with this, but before that, we will essentially be showing that if n is odd, then n squared is odd. So it has to be something like, thus, n squared is odd. So we need to end up with something like this, right? So now if I assume that n is odd, what does this mean? So again, I'm doing that strategy where I sort of look at the beginning at the end and try to meet in the middle. So if I assume that n is odd, then by definition, there is an integer k such that n is equal to 2k plus 1, right? And so again, it's always important to know your definitions. And I'll say this again. If you do not know the definition, then there's no way to write a proof. So when you see that you need to prove something, when you look at this theorem here, and you need to prove it, you need to know the definition of square, you need to know the definition of even, you need to know the definition, I guess in this case, of odd, because you're going to use it. If you don't know the definitions, there is nothing that you can do, so you need to go back and check the definition. Okay, so we're assuming that n is odd. By definition, there is an integer k such that n is equal to 2k plus 1. And the next thing is we can then, we want to look at n squared, so let's look at then n squared will be 2k plus 1 squared, and if you do the algebra, this will give you 4k squared plus 4k plus 1. And the idea here, so what does it mean that n squared is odd? It means that we want to show that n squared, so we want to find, some m, let's say. So something like, thus n squared is equal to 2m plus 1, right? Which by definition means that it's odd. So thus n squared equal to 2m plus 1. So this is our goal. We would like to end with n squared equal to 2m plus 1. So we would like to isolate a 2m plus 1. And if I look at this expression up here, I can do that by factoring out a 2 of the first part, and you get this. And this gives us a candidate for m. So let m equal to 2k squared plus 2k. And now the last thing we need is that m needs to be an integer. So since the sum and product of integers is an integer, then m is an integer. And then, since n squared is equal to 2m plus 1, which is an integer, n squared is odd by definition, and therefore we have what we wanted to show. So let's look at this again just carefully. So we wanted to show that if n squared is even, then n is even. That's equivalent to showing that p implies q, where p is n squared is even, q is n is even. Now, this is equivalent to the contrapositive statement that not q implies not p. And so we want to show this. So since we want to show this, we state we are going to prove by the contrapositive. Now, what does this mean? This means that we need to show that if n is odd, then n squared is odd. So how do we do that? So we first assume that n is odd. Then by definition, there is an integer k such that n is equal to 2k plus 1. But then if you square n, you get 2k plus 1 squared, which gives you this expression here. And if you let m equal 2k squared plus 2k, then this m is going to be an integer, and n squared will be written in this form, where m is an integer, and this means that n squared is odd by the definition. And so therefore, we've shown that if n is odd, n squared is odd, which is this statement here, which is the contrapositive of this statement. So thus, by the contrapositive, this is also the case. And so we just proved that if n squared is even, then n is even.